last thing we did was convert polar points to rectangular points, x's and y's, and then vice versa, x's and y's to r's and betas. So today we're going to use those same four equations, the conversion equations that we were using to convert equations in polar form to rectangular form and vice versa. The first problem we're doing here, this is a rectangular equation, x's and y's, and we want to convert to polar form. So your goal is just to replace any x or y with r or theta, respectively, okay? So x squared plus y squared, I could convert each of those individually, but them together as a whole creates what from yesterday? Do you remember what x squared plus y squared was equal to? R squared. That's just the Pythagorean theorem. So the only other piece that needs substituted here is the y. Do you guys remember what y is equal to from yesterday? There's a theta, r sine. And you want to remember that sine goes with y and cosine goes with x, just like your unit circle. Plus 3 equals 0, and that's it. Okay, so we're not looking for any specific form when we're getting our polar form of our equation. If we were going to put this in our graphing calculator, we want the r to be isolated, but that would be like a whole nother thing that we don't really get into in this class, so we just leave it like this. Okay? All right, what we're going to spend a good amount of time on now is taking polar equations and putting them into rectangular equations. And rectangular equations with x's and y's should then be something that we recognize and we're able to graph from actually like college algebra last semester. All right, so let's start with r equals a number. R equals 2. What is r equal to? What can I replace it with in terms of x's and y's? X squared, well, r squared is equal to x squared plus y squared. So what's r equal to? It's, I can't do that, but I can say the square root of x squared plus y squared is what r is equal to. Okay, and then I can't take the square root there because of that addition. To make this graphable, I'm going to square both sides to get rid of the square root. So that would give me x squared plus y squared equals 4. And then that is the standard form of an equation that you should recognize. Does anybody know what this will look like when I graph it? This is a circle. Can you tell me what the center of the circle is? Okay. Yep, it's the numbers that are subtracted respectively from the x and the y, which there's nothing next to those, so 0 and 0. And then the radius is the square root of the number that's alone over there. So the square root of 4 gives me 2. Okay, do you guys remember that standard form? Maybe I'll write it at the bottom here just so we have it. It was x minus h squared plus y minus k squared equals r squared. That was a circle. HK was the center, R was the radius from last semester. Okay, so R equals 2, when I convert to polar form, ends up being a circle of radius 2 centered at the origin, which we can graph. So I make my center at the origin, I go 2 units in every direction, and I have my rough sketch. Oh, that froze, there it goes. Okay? Questions on the first one there? Okay, second one. This one just has a theta. Theta equals negative pi over 3. Again, I'm trying to convert my theta to x's and y's respectively, and we have one equation that converts a theta to an x and a y. It's our tangent equation. If I have tangent theta, I can replace it with y over x. That's one of our unit circle ratios. So the first thing I'm going to do with theta equals negative pi over 3 is take the tangent of both sides so I can use that formula. Come on, there it goes. And again, tangent is equal to, from your unit circle, y over x. Okay, so that gives me my rectangular piece. Tangent of negative pi over 3 is something you can simplify. The negative angle, can I get rid of it or bring it out front? Bring it out front. Tangent is odd. Okay, does anybody know what the tangent of pi over 3 is equal to from your unit circle? It is square root 3, whatever, yeah, that's right. Okay, and then this isn't quite a form that we're familiar with. Normally, if we don't have both x and y squared like that last one, we try to get the y alone. So I'm going to multiply both sides by x to get my y alone. So my final answer here is y equals negative rad 3x. Okay, now that rad 3 is kind of gross. That doesn't really matter. Imagine it's just a nice pretty whole number like y equals 2x. What is this? What am I graphing? This is a line. And there's two things that you should know about a line. You should know the slope and the y-intercept. What's the slope? Negative rad 3, and the y-intercept is 0. So I can graph that. Make a point again at the origin. And then negative rad 3, I'm going to have to go down rad 3 over 1. Rad 3 is about 1.7, if that's helpful. So I'm going to go down about 1.7, right 1. You can do that a couple times if you need to. And there's your line. So what ends up being interesting about this is I actually get a line where negative rad 3 would be at if I did that rotation. This rotation right here is that negative pi over 3. It's negative 60 degrees. So you're seeing this ray show up wherever that theta was located at. So that's a nice way to check those ones. Okay? Questions on either of those? Okay, we've got two more of these just so you can have an example of each one in your notes. R equals secant theta. Oops, too far. R equals secant theta. Okay, so secant is not one of my conversions formulas, but what is that's really similar to secant? Let's write it as 1 over cosine. Okay, so R equals 1 over cosine. Okay, and then how about we get that cosine out of the denominator just to make it a little prettier? So I'm going to multiply both sides by cosine. R cosine equals 1. Do you recognize R cosine as one of our formulas? What is R cosine equal to? It's equal to, close. There's no 2 at all. How about just x? R cosine is equal to x. That's one of our formulas. And that's it. We're done. What is that? X equals 1. It's an up and down line. There we go. It's a vertical line at 1. Okay, and if you had y equals a number, it would be a horizontal line at that number. So we can graph that really easily. Make a vertical line at 1. Okay. All right, last one. R equals 2 sine theta. There's that 2 you wanted, James. Not that one. Okay. All right. So I have a sine, which is good, but there's not an R next to it. If I had an R sine, I could replace it with Y. And I have an R, which is okay, but R squared would be better because then I wouldn't have to deal with the square root. So if you see that having an R on both sides would be helpful, that's a good place to start. Multiply both sides by R. So I'm going to get R squared equals 2R sine theta. And that makes it easier for me to replace things. R squared is equal to what? X squared plus Y squared. And R sine is equal to 2Y. This again is a circle. This one is not in standard form though. So you have a couple steps to complete the square, which we did last semester, to put it in standard form to be able to graph it. To put it in standard form, you want all your terms on one side with your x's and y's. So I'm going to move that y over. Okay, it's going to be a minus 2y. Okay, now the x I don't have to complete the square with. I can just write x minus 0 squared and that guy's good. Okay, the y's are where we have to complete the square. To complete the square, you take the number in front of your y, in this case, half it and square it. Remember, that was the completing the square step. Half it and square it. So if you need to make a note to yourself, that's what I would write down. Half it, square it. So if I take -2 and half it, square it, what would I add on? Half of -2 is -1. Square it would be a +1. And we have to add it to the other side as well to keep my equation balanced. Now that y squared minus 2y plus 1 can be factored. What does it factor to? Y. It's something squared. The other side's going to be 1 minus 1 squared. And now hopefully you see that standard form of a circle. You should be able to tell me now what's the center. 0, 1. So it's the opposite of the signs that you see inside the parentheses. And then the radius is the square root of the number that's on the right side there. The square root of 1 is still 1. So we have a circle centered at 0, 1. I can plot that point with a radius of 1. So I'm just going to go 1 in every direction to get my circle. And it's going to look something like, oh, that's a bad circle, but you get the idea. Something like that. Okay. All right, so that should be one of every example that you're going to see on the homework then. So if you get stuck on one of these where you have to convert it, look at these 4 and see if you can see one that's of a similar form to start. And that should kind of help you with where to go from there to be able to convert it. Okay, any questions on those 4 problems? Okay. The last one we're going to do, and then we're going to check all the answers you guys did in the packet day before yesterday, is we're going to do a graph by hand just so you can see kind of where these graphs that you made in the graphing calculator are coming from. We don't spend a lot of time on this. It's literally just plotting polar points, filling out a table. We're going to spend more time really just being able to see it in your graphing calculator and check answers that way. But I wanted to show you at least one of these where this came from. So let's do the one on the left. We're going to graph the polar equation r equals theta. Okay, so instead of an xy table, we have a theta r table. Theta can be any angle you want. Typically, we're going to choose radians are going to be easier. And a good place to start, especially when we don't have like super complicated equations, are just those special radians as we go around our circle every 90 degrees. Pi over 2, pi, 3 pi over 2, 2 pi, maybe we'll get one more, 5 pi over 2. Okay. Now normally we plug that in for theta and get the r, but in this equation r and theta are just the same thing, it's telling me. So my r's will also be 0, pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. Okay, now plotting them, you can label the circles whatever you want, just like when we have a normal XY axis, we can label it whatever we want. When you did the activity, you labeled it 1, 2, 3, 4. Here, we've got to plot things in terms of pi, so that's why it's labeled in terms of pi. 1 pi, 2 pi, 3 pi, 4 pi, those are the radii of each of these circles. When I graph 0, 0, of course, that's my origin. Remember, we called that the pole yesterday. Then, when I graph pi over 2, there's 2 things I have to think about. Number 1 is the rotation. So pi over 2 would take me to what looks like the y-axis here. And then the length or distance from the origin is also pi over 2. So if the first circle is pi, and I want pi over 2, I'm just going to be halfway between the pole and the first circle. Okay, so a pi over 2 rotation takes me to the top there. Pi over 2 length takes me halfway to pi, the first circle. So my point is going to go right there. Okay. Then pi, pi. Okay, so pi would put me on the first circle out, and then a pi rotation would put me on the left side of my axes there. So on the first circle, on the left side, right there. Okay. 3 pi over 2, 3 pi over 2. So 3 pi over 2, we know my radian measure takes me to the bottom here. 3 halves is halfway between 1 and 2. So I'm going to be halfway between the first and the second circle, and you guys are going to see a pattern. Every quarter rotation, we're just getting a half a unit further away from the pole there. So 2 pi would be back on the axis. 5 pi over 2, I would rotate another 90 degrees and go another half unit out, so on and so forth. Then, to create the pretty graph, we connect those points in the order we plotted them with a smooth curve. And this one's called the spiral of Archimedes. So the spiral is one that you guys didn't have in your packet, but this is how you would get a spiral. The next one is also a spiral on the right there. It's just a little wider because there's a 2 theta. So it's not as tight of a spiral. It's a little looser when you draw it. Okay. And then you can get really involved with like the ones that look like flowers. We call them rose curves, things like that. All right. Questions on that? Okay, do you guys have your packet from yesterday that you got back? That's the last thing we need to do is correct those. Okay. If you're looking at your Jamboard or the notes online, I took some pictures out of your textbook for what a lot of these official names are. So limacon, there's a few different ways it can look, and we'll talk about that in the packet in a minute. You guys saw rose curves, circles. One that we didn't see was a lemniscate, kind of looks like an infinity symbol. And then the spiral we just saw a second ago. All right, so to that packet, I didn't capture on here the graphs that you guys made. I just captured the, and it's a little dark, but you get the idea. I just captured the answers on the bottom of each page that you were supposed to kind of figure out based on the pictures that you were sketching. Okay, so number 1 on the first page, you should have put a circle there. The A value, the number out front, represents the diameter of the circle. Number 3, there's a few ways you guys could have worded this. I said above the x-axis and to the left of the y-axis, but if you said quadrants, that would have been fine. So like the first part, if you said quadrant 1 and 2, that's good. The second part, if you said quadrant 2 and 3, that would be fine also, however you want to describe where that was located at. And then without a calculator, hopefully you were able to draw these two. If we have a sine, it's going to be above or below the x-axis. If we have a cosine, it's going to be left and right. And then the number in front tells me the diameter. Positive or negative tells me again whether it's above, below, or left or right with those. Okay. All right, page 2. Okay, so officially these are called rose curves. Instead of flower, that's fine. The A value, the number out front, is the length of the petal, and the B value helps you figure out how many petals there will be. So hopefully you notice in the graph, some of them had that exact number of petals, and some of them had double the number of petals as the number you saw in the equation. And that has to do with whether it's even or odd. So if it's odd, it has that exact number of petals. So if B is 3, it has 3 petals. If it's even, like if B is 4, it has double that number of petals. If you look back at those pictures. Okay, and then the difference between a sine and a cosine is very distinct. It's just a rotation of 45 degrees, one from the other. The easiest way to tell the difference, I think, is if it's a cosine rose curve, you're going to have a petal on the x-axis. If it's a sine rose curve, you will not have a petal on the x-axis. On the right there. Okay. Good there? Okay. All right, on the third page, I definitely did not think that you were going to name number 10 that. Called it a heart or a circle with a dent in it, whatever, that's fine. Okay, it's called a cardioid officially. A limacon is the group of these that can look different ways. The ones I just labeled from the pictures above, which ones had an inside loop and which ones didn't have an inside loop there. So any of them from above you could have written, but A, B, C, and H had an inside loop, D, E, and I did not. And then hopefully you figured out if A is smaller than B, it has the inside loop. If A is bigger than B, it doesn't have the inside loop. And it has to do with the sum and the difference of those numbers are going to be how wide it is and how far in the inside loop goes. We don't get, again, too complicated with these, but that's just kind of something maybe you noticed, the sum and the difference of those numbers. Okay. Good. And then on the back, these were the top equations, which hopefully you were able to do some of this without a calculator. These four are the toughest ones, all the Lima sons, the ones that have an inside loop or are dented or look more like a circle or a heart, that sort of thing. The ones at the bottom maybe should have been a little bit easier. You can scroll down a little bit there. Okay, these were the ones you could identify more from what was happening in the packet. Number 7 and 9 we did in class today. Kind of talked about circle radius 2. We actually graphed that exact one. If you see a line, that's the only one that really wasn't in the packet at all. That is just a theta equal to a number. Okay. All right. And then that is everything that you need to know about polar equations. So plan for the next couple days. First of all, your 7-6 Math Excel is due on Friday night, so that's your next deadline. Tomorrow in class, we're going to do all of 7-7. It's a shorter section. And then Friday will be a Math Excel work day for you to work on 7-6 and 7-7 if you want. Okay? And then on Monday is our last quiz. Monday will be open note partner quiz on 7-6 and 7-7. Everything from this week. Good? Any questions for me? No, great. Okay, I'll do cell phone lotto, and the last 7 minutes here are yours.